Over 50,000 of you watched video 3. That is unbelievable. Never expected this. Thousands of you left comments. Some amazed, some were skeptical, and some of your comments were calling me out. Two biggest pushbacks were, Chris, a solar system doesn't look like an atom, and those numbers feel cherry-picked. You're right on both counts, and that's exactly why today matters. So today I'm going to answer those questions directly. I'm going to show you the full data set. I spent this last week fighting with the statistics. I'll show you the statistics run live, and I'll correct one thing I said last time that I got ahead of myself on. So I've uploaded everything on GitHub. So it has the data, the code, the figures. I wrote a very detailed PDF paper, so scientific paper, if you will. And so you can check all that out for yourself. Let's dive in. So first, the big one. Solar systems don't look like atoms. Electron clouds aren't planetary orbits. Absolutely correct. They don't look the same. Just like a single cell from a whale doesn't look like the whole whale. So one's microscopic, made of biochemistry, and the other's a 100-ton animal with organs, blood vessels, and a nervous system. So they're completely different structures. It's different physics involved. There's different forces acting on them. But both of them do the same thing, right? They both metabolize energy. They both maintain their organization. They both respond to the environment. They reproduce. They go through evolution. So what I'm saying is it's the same organizational principles across different scales. So you have different implementation based on the actual scale or dimension. So that's what I'm comparing here. So it's not the shape. It's not necessarily the same forces. You have the proton at 10 to the minus 15 meters. It's a dense energy core, right? It's organizing an extended electromagnetic field around it. You have the sun at 10 to the 9 meters. It's a dense energy core. It's organizing an extended gravitational field around it. So you have different substrate, different physics regime, but you have the same architectural function. You have a centralized power source holding a stable system together. If they looked exactly identical, critics would say, of course, it's the same physics. The fact that they look completely different, but organized the same way across 10 to the 24 meters, I think that is the interesting part. Okay, now for the second critique, right? You cherry-picked or rounded the numbers to force the pattern. You cherry-picked these numbers. They're not special. And honestly, that's a fair question. I asked myself that thousands of times over the last 18 months. But here's exactly what we did. So I'll show you. There's no hiding, fully transparent. I noticed that organism complexity seemed to increase roughly every 10 to the 3 meters. I noticed it from the EMF spectrum. If you know that graph that shows the EMF frequency waves. So you have molecules to cells to organisms to social structures. But the scale always ended at buildings, right? They never went further. So I went ahead and I asked multiple AI systems, right? What are the fundamental organizational structures at these scale intervals? They returned the same canonical list most fields already use. Protons, atoms, ribosomes, bacteria, multicellular organisms, humans, cities, Earth, sun, solar system, open clusters. That was added from Oort Cloud. Local bubble. I found that based off your comments. Thank you. Then we go to the Milky Way, Virgo supercluster, observable universe. These are all steps of 10 to the 3 size changes. I cover that in video 1. So no cherry picking, if you will. There is some selection bias, and we definitely need to worry about it. But these are the structures every textbook and survey already recognizes. Then we tested their actual measured sizes for 10 to the 24 separation. And I had comments saying, hey, a human's not 1 meter tall. And it's right, I used radius, but actually it's not 1 meter radius either. Half height should be actually 0.9 meters. We'll talk about that. So yes, your comments did actually make me go back and look at every single source and measurement and reassess it. And actually I got better data. So thank you. And so I found the best way to do it is to have a characteristic length L. So every value is from a peer-reviewed source. So CoData, IAU, Planck, BioNumbers, Gaia Mission. There are things that are ambiguous, right? The local bubble. You mentioned cities. You're right. Open clusters. So for that, we have to show the full sensitivity range. So here is the chart actually from the paper. You can get this again on GitHub. You'll notice the sources, half body height for human. So now it's 0.9. And that's if you have a representative human of 1.8. So I have the local bubble, 50 to 250 parsecs, but it depends on the tracer and direction, right? Because it's not a regular shaped object. And even at the upper end, it's still 0.89, still good. So I didn't pick the value that makes it perfect. I picked the conservative one and then showed the full range under the sensitivity notes. Okay, now for the most important part. Is this just a coincidence? And we ran the right test, a permutation test. I'm running it right now live so you can see it. So it's not random adjacent pairs. That was an earlier mistake. But this test does exactly what we need. It takes our 15 measured sizes, randomly shuffles them, then it checks if our predefined pairs will still show 10 to the 24 matches. Repeat it 200,000 times with a fixed seed 42 so anyone can produce it. So this is it right here. It's running the Python code. Okay, and it gives a result. So you have a p-value 0.000055. Number of successes was 11 out of 200,000. That gives a statistical significance of 3.9 sigma. So that is highly significant for pattern analysis in complex systems. And like I said, the data is all there, link in the description to the GitHub. You can go run the tests for yourself, and please let me know if I did anything wrong. So see, this is the histogram. So most random trials get 0 or 1 strong match. So our observed value of 3 is way out in the tail. Okay, and that's why you're getting a sigma of 3.9. Because there is a chance it could be coincidental, but it's very low. So your significance is 3.9 sigma, chance that it is not random. And to be extra conservative, to shut down any arguments that I picked 24 because I saw it first argument, I did a look elsewhere correction. So this scans every possible delta from 22 to 26. So find the best value and then test how rare these strong matches are, even when you're cheating. So the best cheating delta gives 4 strong matches, but even then, that's only 1 in 200,000 random shuffles. So that's if you're cheating. So the pattern basically survives the toughest statistical scrutiny I could find. Anyway, again, please let me know if you can find better tests for this. So one thing I do need to correct from last time. So in the comments after video 3, I first had so many views. I'm just so excited that there's so many people out there that have seen these similar patterns as well and think like me. I just thought I was crazy for years, but then I actually looked and found all these amazing patterns and so many comments from you guys. But I got excited about the sigma 8 tension. And that's the fact that the universe is about 8% less clumpy at galaxy cluster scales than standard models predict. And I ambitiously said in the last video, I said I would show how this pattern explains sigma 8 from first principles. And I can't, not yet. I got ahead of myself. Right? I saw the numbers, Kleber exponent 0.75, observed sigma 8 around 0.76, and jumped to a connection. I thought there would be a connection there, but I can't rigorously defend it right now. And that was overreach. So sigma 8 is a real tension. The universe is less clumpy than predicted. Could organizational patterns like the ones we've documented play a role? And maybe. It's an intriguing possibility. But saying I can derive the exact value from first principles, like how it works, the underlying physics mechanism, no, that would literally require new physics, and we're not there yet. But I think it's fine. I don't think we need to. Think about Mendeleev and the periodic table. He documented the pattern. It was elements arranged by atomic weight, showing repeating properties. But he didn't know about electrons, he didn't know about protons or quantum mechanics, and he didn't need to, right? The pattern was real. The mechanism came later. And I think that's where we are now. If this proves correct, I've triple, quadruple, many hundreds of times checked a lot of mind-blowing things already in the book. The scale table, the octave matches, the statistics, and there's many follow-on mind-blowing things that really are solid, and I can't wait to share them with you starting in the next video. But when I get excited about new possibilities in the comments, I sometimes share them before they're fully verified. So lesson learned, I won't do that in the past. So from now on, I'll be much more disciplined, stick to what's rigorously tested in the book and appendices. No more jumping ahead with these exciting connections. I definitely will listen to your comments and we'll take them into account, but I'll make sure that I'm confident they can hold up. And I think we have that. The pattern we have, you have 7 strong matches. You have a 3.9 sigma is already extraordinary enough, I think. So that's what I'm focused on. Okay, so here's where we stand, right? We have a pattern. We have 15 structures spanning quantum to cosmological scales. We have 7 octave pairs and 3 strong matches that only deviate by less than or equal to 0.2 from your ideal ratio of 24.0. So that's on a logarithmic scale. These are huge numbers. And you are statistically significant at p equals 0.000055 for 3 or more strong matches by chance. And that is a 3.9 sigma based on the null hypothesis. And this survives a look elsewhere correction. So these are the 7 octave pairs. It's all based on peer-reviewed measurements, and I refined them as well. So there's full transparency on the uncertainties and the sensitivity notes. So this is an empirical observation that I think deserves serious attention. So does it mean the universe is fractal in organization? Possibly, right? Doesn't prove it. Does it mean there's a deeper principle at work? Maybe. But right now I'm focused on the what, right? Not jumping to the why. So next video, we're going to test whether the same framework applies to something much closer to home. And this is really mind-blowing new stuff I haven't heard before, and that is nations. So using the exact same biological criteria that biologists use to define what counts as a living organism, what do you think a nation scores in our current 2 best tests of livingness in a biological entity? Next video, we're going to score it and see what happens. See you next week. Thank you so much for being here. Thank you so much for your excitement. I am just as excited. I really feel like this is my life's work, and I have so much more to share with you guys. I'm so excited. And go check out the GitHub. I even put you guys in here. Special thanks to our Fractal universe audience for their thoughtful and engaging comments. I think it really did help and push me to make this GitHub, to write the paper and do all the heavy statistics on it. Spent this whole week, didn't sleep that much. So thank you. You guys really are a part of this. And I have to give a special thanks to my good friend, Jenner Torrance. He has a company. It's called frontierstrategies.ai. Full disclosure, I'm actually a partner with Jenner. Thanks so much for bringing me on. He kind of wrangled me, but he taught me an amazing amount about AI. And one of the key points is that you have to force it to actually use calculator code. Make it write the Python script to do the code, because LLMs are not that good at math. They mess up a lot. But if you force them to actually write the code, they're very good at writing code that is good at math. And he helped me a ton make the master math appendix, and with the book get serious analysis. And yeah, I don't think I could have done it without generous help. So check it out. If you do want a strategy session, it's normally $500 and now it's $199. And you also help me now since I'm a partner in the company. But anyway, see you next week. Thank you so much for your interest. Love this topic. So stoked. Peace.